Okay, let's get started with the afternoon session here. Again, I'm John Chapin, and Program Officer for National Radiodynamic Zones at the National Science Foundation, and leading this workshop, or co-leading this workshop with my colleague Chris Anderson. So I think we have critical mass to get started for this afternoon. It is my great pleasure to introduce Austin Bonner, who's joining us this afternoon. She's told me that there's some things happening back at the office, and she's not going to be able to stay for too much time today, but she's going to be rejoining us tomorrow. So certainly enjoy her talk today, and then catch her tomorrow for any informal follow-up questions. So very briefly, Austin Bonner is the Deputy U.S. Chief Technology Officer for Policy. She has been a key player in the development of the National Spectrum Strategy, among many other nationally important issues. Austin joined OSTP from the Federal Communications Commission, where she served as legal advisor and acting chief of staff to Commissioner Jeffrey Starks. Before joining the FCC, Austin practiced communications and appellate law at two leading DC law firms. So with that, I will give you Austin, please. Thank you very much for being here.
Hi, everyone. Thanks for having me. Can you hear me okay? Okay. Well, if you are asking yourselves why a lawyer from the White House has come to talk to you at a conference focused on spectrum R&D, I promise I will explain before the end of the next 10 minutes. As John said, I'm joining you from the White House Office of Science and Technology Policy, where it is a really exciting time to be working on all things telecom, spectrum specifically, and something that our leadership really cares about, and that I'm going to talk about today, dynamic spectrum sharing. OSTP is a pretty special place, in my opinion, in the White House. In 1976, Congress recognized the need to make sure the president gets the very best science and technology advice, and to coordinate the really broad and expansive science and technology enterprise across the federal government, and created OSTP to do that. So nearly 50 years later, OSTP continues to work to maximize the benefits of science and technology to advance health, prosperity, security, environmental quality, and justice for all Americans. I want to thank the National Science Foundation and everyone who worked to organize this special week. So much has changed since Spectrum Week 2023, from the President's signing of the Presidential Memorandum on Spectrum, the announcement of the National Spectrum Strategy, the real achievements of our excellent delegation at the World Radio Communication Conference last year, that I think we have a lot of good work to reflect on. And it's a really good time in our life together to be talking about how we're going to shape the wireless future going forward. You might expect that inside the White House I have a little explaining to do when I talk to people about spectrum. But it's really not hard, I think, to connect what you all are doing here today to really important priorities of the Biden-Harris administration. President Biden believes that every American should share in the benefits of the kind of cutting-edge research that you're talking about and all the possibilities of the digital age. I think for you all, I don't have to do the in-depth explanation about how spectrum is such an important component of things like lowering costs on important telecommunication service that provide a lifeline and a public safety benefit to so many Americans. Things like telemedicine that rely on the connectivity that you all are helping to create to make sure that medicine meets people where they are. Things like climate change, what we're using to forecast and help protect Americans better from severe weather. Things like making sure that our national defense systems are ready when we need them. My boss, the President's science advisor, Arthi Prabhakar, likes to say that practically every part of American life runs on spectrum. I think you all know that, but I'm excited to be able to spread that message around the White House too and make sure that our leaders really understand the importance of what's going on in rooms like this. I also want to say that this work is really driven by the President's commitment to modern, affordable, high-quality internet for every single American. It's really clear from the last few years that internet access isn't a luxury. This is a necessity. It's about education. It's about healthcare and jobs, about all the ways that we participate in today's society. And advanced wireless networks are really one of the ways that we meet those needs. And so I want to commend you all for being part of the effort when we get every last drop out of our nation's spectrum resources, when we improve our wireless connectivity, we're helping to spread those benefits to people that need them and really reach every corner of America. Those efforts also include things you may have heard about elsewhere in our telecommunications discussion, like the Affordable Connectivity Program, that are bringing affordable, low-cost internet to Americans, but also, you know, a program that I'm thinking a lot about this week because it's really time for Congress to extend that and make sure that that good work can continue. So we can't have those advanced wireless networks that reach every single American unless we keep finding ways to use spectrum more effectively. We have to have a forward-leaning spectrum policy, or our country won't be able to stay ahead in the next generation infrastructure. Things that help create critical communications for first responders that save lives, the smart networks that make factories more efficient, and military communications that keep us safe. We face a global challenge in our leadership in spectrum policy, and I think you all know that these questions are really hard. We are out of easy spectrum choices at this time. I think I would love for you all to make them easier and put me out of the job, but that is not where we are today. For the U.S. to remain a global leader in technology, President Biden has recognized that we simply can't fail to make more spectrum available and ensure that we use it efficiently. And the U.S. government, as the biggest user of spectrum, must be in the lead in solving this issue. Thus, the White House convened an interagency process that included our friends at NTIA, at the Federal Communications Commission, the Department of Defense, and other agencies, so that the executive branch could really work together and agree on a forward-looking, wide-ranging national spectrum strategy that will ensure our economy and our military have an edge for decades to come. The strategy contains a lot of elements. It's been out for a little while. I'm not going to walk you through every part of it because I want to focus on dynamic spectrum sharing today. But I do want to start by saying that, you know, we highlight the importance of a pipeline of new spectrum to be made available to commercial use. Regarding that pipeline, we've identified more than 2,700 megahertz of spectrum for in-depth, near-term study to be completed in the next 2 years. The most ambitious spectrum study goal to date. If our friend Charles Cooper looks stressed out by that sentence, you probably know why. But to the point of what we're really gathered here today, I want to make sure that we discuss the second component of the strategy, our focus on dynamic spectrum sharing. We announced an effort in the strategy to use advanced technologies such as AI, edge computing, to enable government agencies like DoD to use spectrum for critical purposes while still creating more opportunities for commercial users. Working in partnership with industry, we're committed to making significant measurable progress on that goal in the very near term. We believe this effort will be critical to prevailing in the strategic competition I discussed before, and because it will enable the U.S. to more efficiently use spectrum, spurring innovation in the wireless space. And such innovation will have applications for both the commercial, defense, and other agency sectors. So what are the objectives of our DSS effort? I think there are at least 5 things that we're trying to accomplish, and I know as you all continue to engage in the process, we may find more goals. First, I want to emphasize that we want to build a next generation spectrum sharing capability. We are not only aiming to do a report, but to build a prototype that shows all stakeholders, including agencies, industry, civil society, allies, and partners, what we can accomplish to improve spectrum access and spectrum efficiency using cutting-edge technology. Second, we want to make sure we're developing a mechanism that would be an improvement on the automated frequency coordination that's already doing good work in the CBRS bands, so that it has potential application to future sharing regimes. This involves identifying and implementing improvements in automated frequency coordination, which can be initially used in CBRS and applied to other bands in which there's a similar capability is needed. I think there's a lot of good possibilities here. We've talked about, ways to improve sensing, ways to eliminate whisper zones, the fine-tuning of our reservation system, a more dynamic sensor-based system. I think there's a lot of options here, but we want to make sure that we've already done a lot of good work. I think NTIA has played a huge role in making CBRS better over time, and we want to look at ways that we can do even better than that in the future. Third, we need to improve the ability of commercial mobile networks to share. This may involve developing separate and integrated base station sensors to detect incumbent operations. This could enable USG to resolve, the US government, to resolve federal use within signal and signal environments. It could enable us in the government to leverage radio intelligence controller components of Open RAN to ensure that spectrum sharing is quickly and efficiently implemented in commercial mobile networks. And it may even be possible for research funding to be made available through some things like the NTIA innovation grants. That's something we're actively exploring because I think this is a rich area of research. Developing automatic interfaces into commercial radio access networks to inform the operating status of base stations is another area we're looking at. Fourth, we need to obtain data on sharing and coexistence involving federal and non-federal users. This will involve exercises to obtain real-world data about coexistence interference, both between different federal users and between federal and non-federal users. Such exercises should, where possible, test a variety of power levels for commercial use to provide complete information about the ability of different types of use cases to coexist with federal use. Some of you know the other part of my job at the White House is I spend a lot of time working on artificial intelligence. I think I've already bugged a handful of you today about the building of data sets that are interesting at the intersection of those two parts of my job. I think there's a lot of good work to do there, but a real gap that we ought to fill in thinking about how to gather that data. Fifth, we're looking to improve security and obfuscation. We need to demonstrate how to manage sensitive systems in a secure environment, and in order to give federal users, including the military, confidence in the ability to operate securely and maintain operational security. Six, we need to refine our enforcement mechanisms. This should include demonstrating the ways that our enforcement agencies that operate in this area are able to identify and rapidly intervene when there's a problem. And finally, we need to look at different economic models of sharing. None of this new technology works if we create a system that doesn't have appeal for operators to actually use it. And so making sure that we're marrying that technical analysis with the economic analysis that really drives businesses to take advantage of this is going to be an important next step. So thank you to NSF and all of our hosts for having me today. I look forward to their continued partnership and yours with the White House on advancing these issues, and greatly appreciate your perspective. I'm looking forward to hanging around as long as I can and learning from your expertise, and I will see you again tomorrow morning bright and early at 8 a.m. Thanks, everyone.
Okay, that's great. Thank you so much, Austin. And now we have a panel led by Martin from the FCC. And we want to bring up the rest of the panelists and get going.
Hello. All right, well, welcome everyone to today's afternoon panel. Even though this is a plenary session here where all the folks are invited, you're still in the area here that we've been discussing the NRDZ facilities throughout this morning, and we'll continue to do so this afternoon. And I think it ties in well with some of the discussion that Austin just had on the dynamic spectrum sharing and data, and the importance of some of the R&D efforts that are going on through NRDZ and other research projects nationwide. So I'm excited to be here today to introduce today's speakers and to facilitate today's panel discussion. For this panel, the title is Accelerating Spectrum Progress Through Experimentation and Data. I'm Martin Doczkat. I work at the FCC. Some of my roles include the administration of the FCC's experimental licensing program, so that ties into R&D pretty closely, and a lot of the spectrum analysis that involves good quality data. So experimentation and data are two of my major focus areas, which is one of the reasons why I'm here today. So I've been involved in some of the past Spectrum Week discussions, as well as some of the past NRDSCOM discussions. So personally, I'm a big fan of NRDS, so quick plug there, and just like to think that since I'm in an area such as spectrum, that I consider myself to be one of the nerds, especially as an engineer. So for those of you who may be unfamiliar with what NRDS stands for, it stands for National Radio Dynamic Zones. It's part of NSF's Spectrum Innovation Initiative. It's an interdisciplinary program that seeks to foster collaboration among spectrum sharing researchers, like all of you here today, to advance the use of dynamic spectrum sharing and involve spectrum managing practices nationwide. The main concept of NRDZ is the radio dynamic zone, which is an area or a volume, if you think of it that way, that features automatic spectrum management mechanisms to control electromagnetic energy within that zone. These concepts will be tested at ad-scale research and field trials and eventually deployed as permanent, highly capable national radio dynamic zones somewhere in the United States. So during this panel, we'll be discussing how experimentation and data fit within ongoing federal and industry R&D initiatives. In particular, in the context of NRDZ, we'll be considering ways which this research can be most impactful to ongoing spectrum policy discussions. From the FCC's perspective, we've been working for some time in close coordination with our colleagues at NSF and at NTIA as part of our memorandum of agreement with these agencies. Additionally, the FCC has been providing an active supporting role in developing and implementing the National Spectrum Strategy, which we've heard about multiple times today, including NTIA and relevant stakeholders and some of the band studies that are going on. Working on the National Spectrum Strategy also includes initiatives like building the spectrum pipeline, implementing long-term spectrum planning processes, working toward development of a national evidence-based spectrum decision-making methodology, part of which includes relying on quality data. Underlying these efforts are the needs for accurate data to inform spectrum studies to ensure that the spectrum is being put to its most efficient use while still protecting incumbent operations. So we look forward to continuing these cooperative arrangements and discussions to ensure that spectrum continues to be used in the most efficient, cooperative, and technically innovative manner possible. The FCC itself has taken similarly numerous steps to re-examine ways in which it could improve its own processes, from identifying new policies and technologies to improve efficiency, to modernizing its own data collection efforts to gain a better understanding of how its spectrum is being used. Examples of this includes the FCC's recently published Spectrum Policy Statement on spectrum management principles for transmitters and receivers, the FCC's proceeding on promoting receiver performance, and the FCC's technical inquiry into spectrum usage data to advance its understanding of non-federal spectrum usage. These efforts have specifically acknowledged technological advancements such as smart filters and antennas as a means to unleash new and innovative services without unnecessarily restricting existing operations. We plan to further explore ways which modern technologies like artificial intelligence and machine learning would allow us to gain a more sophisticated knowledge of real-time spectrum use. We also note that the spectrum environment is becoming increasingly crowded, and avoiding interference is challenging in a constantly changing RF environment. Therefore, proactive mitigation strategies should include system design to minimize the interference potential. We at the FCC are excited about seeing the fruits of success of the R&D efforts going on, such as NRDZ, working together with NSF and NTIA to improve spectrum efficiency and coexistence, leveraging new and innovative technologies to explore forward-looking sharing opportunities that it may have never been dreamt of previously. The FCC places a big emphasis here on our partnerships with NTIA and NSF and through researchers and industry, because we certainly can't do this alone. We need the support of federal researchers, federal research granting institutions, the private sector to identify key funding innovation areas related to smart spectrum management technologies to ensure that the research into coexistence models and resiliency of both transmitters and receivers have the biggest impact on spectrum efficiency, and that we're intelligently utilizing this scarce resource. So I look forward to our discussion today to explore these opportunities, and with that, turn to our panelists. So here we've got Scott Patrick from NTIA, we've got Wade Mueller from USSTRATCOM, and we've got Doug Hyslop from CTIA. So why don't we start with some opening remarks from the panelists. We'll start with you, Scott, please.
Sure, thanks. Thanks a lot, Martin, and thanks to NSF for inviting me here today and inviting so many NTIA folks. It's awfully nice of NSF to give a platform for us to talk about the National Spectrum Strategy, the implementation plan that followed. These are, it's important that NTIA get messages out, information out. It's not always easy from where we are, and this is great to be here and to talk about these things today, and especially on this panel, it's equally kind of NSF to dedicate a panel to experimentation and data. It's, you know, the national spectrum strategy got a lot, I guess the shorter term goals like the band studies get a lot of attention, but the spectrum strategy was filled with other pieces that involve longer term goals about experimentation, and especially as Austin was referring to earlier, about dynamic spectrum strategy. And you know, it's important. I'm very appreciative of NSF to give us the platform to discuss that. You know, it's driving innovation is not easy. It's a you know, there's lots of research about research, right, about how these things get done and how what works, what doesn't work, and it's hard. It's very hard to make these things happen. But one important piece is kind of grabbing the mind share, and we've been fortunate in this administration with Austin and her team to have really, I won't say create, but you know, but for that kind of support, it's hard to imagine the strategy coming out in such fine form. So getting that kind of mind share, getting that conversation out there is, well, it's kind of two edges sometimes, you know, even now, and I say this with all, you know, respect and generosity, but I can see some things, some language from the Hill come across, and it sounds like that maybe they were the ones who invented spectrum sharing, and so that's okay. It just reflects, if we've got the mind share out there, they're thinking about it, they're talking about it, that's okay. So we'll go there. So these are, I'll just, one more thing, just to kind of level set, and I know everybody knows this, but it's like, you start out, I mean, one of the reasons spectrum sharing is important and why these experimentation and data is important is, as Austin said, that there aren't easy answers anymore. We've reached that point. So Austin said it great, you know, help find those easy answers, and then, you know, Congress might take your ideas too. So,
Thanks, Scott. Wade?
Great. Yes, I'm Wade Mueller, and I'm the Senior Technical Advisor to the Joint Electromagnetic Spectrum Center at USSTRATCOM. And so the one thing that's to note is that, you know, coming here from STRATCOM, I think is a very important thing for, you know, all of you to understand, is that within the Department of Defense, we have long recognized the strategic importance of the spectrum. But I would say that as we're going through kind of a revolution right now in looking at spectrum and the uses of spectrum and sharing spectrum and all those kinds of things, the Department of Defense is also going through a revolution in the way that we look at spectrum. In particular, one of the things that happened just a year ago is we did stand up the Joint Electromagnetic Spectrum Operations Center at USSTRATCOM, and that was a very significant you know, moment within the department. And the reason being is because that organization now is led by a two-star general, Major General Anne-Marie Anthony, and she is now probably the most senior advocate for all things spectrum that we've ever had in the Department of Defense. And so it's been a very exciting year. She just recently actually got to put on her second star, and I'm fortunate to be working for her now. So that's the importance to the Department of Defense. And then looking at the situation that we have, you know, a lot of folks are probably, you know, well aware that, you know, in the department, we've had the luxury of existing in certain parts of the spectrum for quite some time. Now looking at the National Spectrum Strategy, an opportunity to, you know, use different parts of the parts of the spectrum that maybe we've had that exclusive access to. You would think that we would be very, very fearful of all those changes, but in reality, we're not. We actually are pretty excited about you know, this opportunity because of the potential for the new technologies, the things that can help us, you know, be more efficient in the spectrums, the things that are going to help us be more survivable. Because even though that we might have some interest from now the civilian sector, the private sector to commercialize certain portions of the spectrum. Well, the portions of the spectrum that we existed in and kind of had that exclusive access to, well, we had the exclusive access, but obviously adversary nations, looked at those portions of the spectrum and looked at ways that they could try to take those away from us. So forcing us to look harder at our systems and figure out more dynamic ways of using them, help us in that, contested environment as well. So that in particular, from an operational perspective, from USSTRATCOM's perspective, is very important to us. So when we're looking at the experimentation for the dynamic spectrum sharing, the coexistence, all those opportunities to make our systems that much more effective in whether it's a congested or a contested environment are very much of interest to us.
Thanks. Doug?
All right, thank you. I'd like to thank the NSF for giving me the opportunity to participate here today. We're all very passionate about spectrum, and CTIA certainly shares that passion and interest. As the famous Wayne Gretzky once said, you miss 100% of the shots you don't take. This thought applies to spectrum too. You miss repurposing 100% of the bands you don't study. So we're very grateful that NTIA has some good bands teed up to study this fall. As we dive into that work, experimentation and data will be the key to getting it right. As the Wireless Trade Association in the US, CTIA, and our members strongly support thoughtful experimentation and a data-driven process for studying spectrum bands, such as those in the National Spectrum Strategy. Our recent history of bringing the C-band to market shows how this can be successful. Industry and government recognized that the satellite spectrum was underused. The satellite companies studied transponder occupancy and identified technologies to improve capacity. The FCC set up the financial means to allow the incumbents to repack, and this industry-government collaboration brought 280 megahertz of spectrum to market. The C-band auction brought in a record $81 billion in revenue and nearly $10 billion in relocation payments to the satellite incumbents. This same collaboration must be brought to the lower 3 and the 7-8 gigahertz studies. By clearly understanding the incumbent systems and how and where they work, industry and government can collaboratively identify a plan that works for all. Measurements will be an important part of this process. The first step in assessing a band is to measure spectrum occupancy. By where are the systems used today, how often are they on? NTIA has a lot of experience in measuring spectrum occupancy. 12 years ago, NTIA measured all bands below 10 gigahertz in Denver, San Diego, and Chicago. Other NTIA campaigns documented the federal operations and occupancy in the CBRS band. Further measurements of lower 3 and the 7 and 8 gigahertz bands may help identify portions of those bands to repack and clear. And where spectrum cannot be cleared of incumbents, the measured data can help define sharing opportunities in time and space. The second step in assessing a band is to measure incumbent equipment performance in an interference environment. Real-world measurements show what is possible and help fix the main issue that crops up with a purely paper study, which is the margin bug. A paper study attracts margins like moths to a porch light. A dozen different inputs each have a margin applied, such that by the time the study is done, this margin bug has thrown off the results by a factor of thousands and created a situation that would never be encountered in actual operations. Only by grounding a study in real-world measurements and conditions can we succeed in supporting incumbent operations while boosting the economy and bringing more full-power licensed spectrum to the marketplace. We look forward to working with NTIA to employ this data-driven approach in future studies. Together, we will complete the studies faster with greater accuracy, far less ambiguity, clearing the path for actionable progress. I look forward to discussing this further with my esteemed panelists. Thank you.
Thank you. All right, so let's shift gears a little bit to some questions. So focusing on the first word of the title is experimentation. So I've already mentioned about the NERDS concept, and there are a bunch of other R&D initiatives going across the US here. So programs like NERDS, they're striving to push dynamic spectrum sharing to its limits, putting everything on the table from federal to non-federal users, active and passive systems. So it's a complex problem. What do you view as impediments to experimentation? such as the NTIA's Red Book, Section 711, or the FCC's Experimental Licensing Program, that might hinder R&D areas. Anybody can answer.
Well, I'll start out by saying one impediment would be if I didn't mention this. I want to put a plug in for funding opportunity out of NTIA. I think it's already been referenced. And there's a meeting tomorrow, I believe. Somebody can give me the details at MITRE that will...
Starts at 10, runs till 1 o'clock.
Beautiful.
MITRE and McLean. You have to be pre-registered.
So,
But you know about participate remotely.
and participate remotely. But so that would be an impediment if I didn't mention that. So please, those of you who are interested, get out, get to the, if you need to, maybe you're already up to speed, but funding opportunity is a big deal. So there's one. Section or 711 of the Red Book, yes, is kind of the existing place to try to experiment. I think the National Spectrum Strategy, and I think we may talk about this a little more later, provides some ways forward from that to you know, expand opportunity, get people thinking about what these experiments should be. I think the you know, there's the sandbox, there's the test bed, the sandbox, right? The sandbox means for anyone, test bed, come and get your act together, and then you can do a little bit more. These are parts of the spectrum strategy. These are things we're going to promote. But if you're ready to go now, you know, 711 of the Red Book kind of sets forth what can be done and where and so forth. So these are things we're going to talk about. We're talking about it today. We want to make sure that we take advantage of these opportunities.
Yeah, absolutely. I think the 711 portion of the Red Book is extremely valuable, obviously, because that gives us a lot of flexibility. And, you know, obviously one of the end results, I'm hoping, of the dynamic spectrum studies is that we can revise that section in the Red Book in general even more to where that the way that we do get frequency authorizations now can be done in a more dynamic way. We can be looking at more than just simply, you know, frequency separation, but even more sophisticated looking at time, spatial, all different kinds of factors to actually deconflict uses of the spectrum for certain experimentation, and then also for even just general use. So I'm hoping that a lot of the ways that 711 gives us some flexibility now that can actually expand to the rest of the Red Book, you know, at the end result. But impediments in the near term, though, I would say still are our frequency, you know, authorization process. And so some of the things that we are attempting to do within the DoD is give certain areas that are known, you know, good locations to do tests and experimentation, some more blanket authorizations to conduct, you know, certain kinds of, you know, uses of the spectrum. So I think earlier I heard a really good presentation from INL. That's one place that the Department of Defense definitely utilizes the, you know, wireless, you know, experimentation environment out there, and that is a very effective place to do those kinds of things because of some of their natural geography that you know, allows you to do a lot of interesting things in the spectrum. So having some more blanket authorizations for places like that. There's other places in the country that we're looking at that we want to be able to do that. That would be extremely helpful. So getting over some of those internal policy things to allow us to do that.
I think Wade and Scott covered that pretty well.
What was that?
I think Wade and Scott covered it pretty well.
Okay, great. All right, thanks. Yeah. Okay, so I guess another focus area here is data. You know, what you know, when we're talking about experimentation and research and development efforts, you know, I guess one of the questions is what would be relevant data? What data could be useful to whether it's federal stakeholders or to industry or to the Department of Defense? What data should researchers consider collecting while they're conducting these experiments?
Maybe I could just mention that more as a baseline. You know, we talk about spectrum sharing, and I mean, I think most folks here are familiar with CBRS, and CBRS generates a lot of data, throws out a lot of data, and NTIA released last year a report, accumulated a lot of the data that the SASs were very kind to share with us, and we appreciate our SASs, and I know some of you all are in the room, so shout out to you all. You know, that it's expensive to collect data, and so I think thinking about it on the front end is helpful. So and that's one reason why I'm answering the question this way. It's like, you know, when you look at what NTI collected in that report, you try and, you know, in advance, don't have some kind of like preconceived notion, or maybe a limited preconceived notion about what the results are going to be or where they're going. I mean, it was you know, it supported some of the views or a lot of the views that this was growing, it was successful, and then there were surprising results, and you should be open to them. Like it was CBRS is being very much embraced in rural areas. I wouldn't have anticipated that as much, but you can, if you look at that report, collecting of the data, seeing what was growing, seeing where the needs are, seeing what works, try to see what doesn't work. I mean, that's kind of a baseline. And like I said, just to repeat myself, but it is expensive to collect this stuff.
I would say spectrum consumption. So if you look at there's an IEEE standard for spectrum consumption modeling. I think Dr. John Stein produced that, and that's extremely important to us. And the reason being is because I think it's the ability to you know, visualize not just a single problem in the spectrum or a small portion of the problem, but be able to look at you know, the spectrum more holistically, but still efficiently. And that's a very difficult thing to do, but the best efforts that I've seen so far is what Dr. John Stein has done with the spectrum consumption modeling. That, and then also I would say, you know, to be able to model and to detect very low power type signals, because a lot of what we can do in dynamic spectrum sharing will be leveraging things like spread spectrum, you know, direct sequencing, those kinds of things, to be able to extract out, you know, intended signals. And so I would say, you know, things that help us model and identify those things, and that is one of the things that research-wise that we're going to be funding from StratCom with Dr. Veron from the University of Nebraska at Lincoln in particular, because he's done a lot of really good work in you know, being able to identify those signals at a very low power level. So those are the kinds of things I think would be important.
I think when you set out to collect data, you need to understand what it is you're observing first and foremost, and make sure you carefully think through the plan of what you're going to do to collect the data. And you know, the NTIA reports I mentioned earlier are an excellent source. They thought through many of the issues involved in how you collect data, especially of spectrum occupancy, because if you're looking at the collaborative engagement capability system in upper 4, for instance, it's a very persistent transmission. So it looks a lot more like a 5G type of system, and it's much more familiar to those of us in the commercial sector to measure, whereas radars are, you know, a different beast. They're very rarely transmitting. It's a different process and a different way of thinking when you go out to try to understand what's really in use in a particular city out there. So definitely think through how you collect data, and then what you do with the data in terms of processing and understanding if you've done it correctly.
So another topic we can't, you know, Scott mentioned the National Spectrum Strategy, and I don't think we can have a panel today probably that doesn't involve some mention of the spectrum strategy, but you know, there are concepts such as the sandbox that was mentioned, the dynamic spectrum sharing demonstration, you know, national test beds, all sorts of examples of aspects of the strategy that involve collaboration through research. What would an ideal sandbox or DSS demonstration or test bed look like?
Well, I mean, one ideal is like Austin mentioned earlier, is it'll be great to get a prototype, right? We'd like to see that. That's an end goal. Yeah, how we get to there, and mentioned already, there are impediments. I think it's incumbent on us at NTIA to be mindful of the impediments, to try to get rid of those, minimize them, so that good ideas can go forward. The sandbox and the test bed. I mean, I think you heard these discussion of this already, especially involving our colleagues at ITS, who are well positioned to, I don't want to say oversee, but provide, you know, a place for these kinds of still want to say prototype, but get us to the prototype. So these are important. You know, the focus, the spectrum strategy tends to focus on the lower 3 gigahertz. That's where a lot of work has already been done. It would be a place where there would be a lot of fruit to yield. So, you know, that would be another piece of that. You know, and I think, just to kind of pull in one more point, we are mindful as well of the security piece. I mean, it needs to, the prototype needs to be something that is, you know, opens itself up to, no pun intended, to a security mechanism. It has to be secure. People have to be able to rely on it. We're mindful that that's an important piece. So I think that would be an emphasis.
Yeah, I think the most important thing is an environment that would give us the ability to obviously test under multiple conditions. From a DoD perspective, you know, where, you know, obviously we, you know, fear, you know, encroachment upon certain parts of the spectrum. The place where I probably fear it the most is anything that affects our satellites, you know, satellite communications, all of our satellite sensors, and obviously the Department of Defense relies upon those, you know, quite a bit. Now, the reason why that's so important is because it's much harder to go and reconfigure satellites, right? You got a constellation up there that you spent billions, you know, trillions of dollars or whatever to put in place. It's really hard to replace those things. So I would need a test environment where I could adequately model and be assured that what I'm testing, you know, gives me good data on, you know, for example, in the X-band, you know, I mean, are these, you know, things that we're planning to do dynamically in the X-band, how would they affect, you know, our satellite communications?
I certainly agree with all that. You know, a DSS sandbox, you need to think about it like a product development process in a way. You need to gather the requirements. You need to understand how the different systems work. As I mentioned earlier, the DSS is going to have to behave differently in lower 3 than it would in upper 4 or in 7 and 8 gigahertz. There's different types of considerations, and so it needs to be flexible. But documenting those requirements, and then doing some initial modeling theoretically, and then moving into a lab test environment to make sure that how you think it's going to work will give you a pretty good idea of, you know, in that controlled environment, whether it will work before you put it out in the field and see if it works in the real world.
Okay. Scott, you mentioned cost earlier about data, and you know, there's been some discussion about improving propagation models and the underlying data that, you know, it's costly to collect. Some of the data sets are relatively old. But it could lead to you know, better quality models. Are there other examples of maybe data that could be collected under leveraging some of these research?
Well, I'm okay with old data. I think that's, you know, I've heard people refer about updating things, but hopefully with a lot of what we do, you know, the physics hasn't changed too much over a few years, so I'm okay with that. And as far as, and then I heard on an earlier panel, Nick Lesort was talking about what we, what he likes is going with MATLAB and trying to be transparent and saying, okay, this is how we do it. There's the link budget. This is what, this step and so forth. So I guess, and then regarding costs specifically, like these funding opportunities are out there. We have the attention. Spectrum sharing has attention of folks. So I just encourage people to take advantage of that as a way to mitigate some of the costs of doing experimentation or collecting things. And but I'm encouraged on that front because I think we're seeing the funding there coming in. I mean, hopefully it'll sustain. I think we're in a good place.
Yeah, data, I've been looking at that, quite a bit from multiple perspectives, in particular within the Department of Defense. Talk about some old data. Our challenge is that if we have a system maybe that we acquired, many years ago, there's no guarantee that the difference in, say, operating parameters of that system would be correctly updated in our various databases. So one of the things that within the department we use a process called the 1494 that some of you might be familiar with to get approval to operate systems, and we report that it's the data that then flows to the NTIA and so forth to eventually get us authorization. There's certain fields on those forms that aren't mandatory, for example. Certain ones that you might think would be mandatory and be important to us today, things like antenna patterns and things like that. So we have a lot of data cleaning up that we need to do to truly understand what our vulnerabilities are and some of our issues, and then also where we could cause interference and things like that. So little things like that, like cleaning up those data collection standards within the DoD and making sure that working with our NTIA partners that that kind of data is collected properly, not only from us, but I would suggest from wherever else they're accumulating data from. We might want to make sure that we have those key parameters going forward.
Yeah, there's certainly a lot of good efforts underway to collect some better propagation data. A couple of topics I think NTIA is working on collecting some better clutter data as well as troposcatter. I know there's two pretty big topics that factored quite a bit in the last paths process, and I think even as evidence of forward progress, the CBRS community recently managed to relax some of the protection areas as well, bringing in some measurement data into the process of defining how large those areas are. So I think we're moving in the right direction.
And if I could just add on to that, I mean, with CBRS, I think we've had something of a luxury. Maybe we'll have it going forward, but CBRS kind of allowed itself as an iterative step-by-step to see problems that emerge and address them, and some of which are the ones just mentioned. Like I say, I think it's been a good process to be able to see problems often unanticipated, to say, okay, this is what we're going to do to fix this one, can apply it to the next one. Maybe we've solved enough of those problems and generated the data as a result to make that a reliable foundation for using in other bands.
So I think we have enough time to maybe open it up to audience questions, but while we do that, just want to float one last question to the panel. Another term that I can't go one panel without hearing about is artificial intelligence. So what do you see as far as AI, ML, and digital twins' role in experimentation and data?
You want to?
Would you like to start?
I'm going to take that first. I almost let Austin answer that. It sounds like she's the one swimming in it. It obviously generates a lot of excitement. I mean, people all over, Wall Street, technologists, a lot of justifiable enthusiasm for AI, and I'm sure some of it will pan out fantastically, and then other pieces of it, you know, are gonna be the subject of late night talk shows. So we'll see. Well, it'll, you know, we're obviously sensitive. We have Alan Rossner is here. We've got a little something tomorrow to look at, and internally, you know, we're doing these things. It's exciting, but yeah, I gotta be mindful of the. We don't have it all figured out.
No, I'm very excited about artificial intelligence and machine learning. I think there's so many applications for it from multiple angles, and so certainly when it comes to the dynamic you know, spectrum sharing in particular, and a lot of the research that we've been looking at specifically from Dr. Varan includes a lot of AI machine learning. What I saw earlier today in one of the presentations was about you know, taking some of our physics-based modeling and then combining that with some of our neural network you know, modeling, and then how you got a much more refined, you know, better picture. Again, to me, that was going along those lines of that spectrum consumption that we're kind of looking for. So I think it has a tremendous amount of use, but obviously with machine learning, it depends on how much data you can feed into it, right? And then how effective you are at collecting that data rapidly, processing that data, and actually learning from what's taking place. So that's a real trick, but I'm excited. I like what I've seen so far, and I can't wait to see more.
You know, they're certainly doing some amazing things. I saw an article the other day, the Air Force had a jet flying powered by AI, so there's certainly a lot of new worlds out there waiting to be driven by artificial intelligence. I'm sure Spectrum will have that place as well. I can certainly imagine how that would probably have made the early days of CBRS a lot less painful for some of my good friends and colleagues who work in some of the SaaS companies who had to do a lot of figuring by hand and with computers that took them hours. Yeah, I'm sure there's a bright horizon there, but it's not an area that I've researched much yet.
Okay. Do we have an audience question?
Thank you. My name is John Moran, professor in University of Nebraska-Lincoln. Thank you for your remarks. In addition to your roles that, as you described, you're also, and your institutions are also employers. And we are, most of us here, educators. So I'm going to have a workforce question. Working in this field, I used to define the perfect graduate student as someone who knows programming and knows what Fourier transform is. And more recently, I added to this for someone who knows the two definitions of transformers, so circuits and AI. So I wanted to ask you, in this current complex environment of where spectrum and wireless research and development is, what are the workforce needs that you see in your institutions, and how can the universities, the education institutions can gear towards educating the next generation towards that end?
Well, I can start out. So when I was, when I was a senior in electrical engineering, I think most of my classmates filled those categories, except for the AI transformer piece. I mean, I think that it's the teaching piece seems to me to be there. I think it's grabbing attention of folks who have plenty of opportunities, trying to wedge our way in and say, yeah, well, this is an exciting and important field. And I mean, the workforce piece, which was also a part of the spectrum strategy, Pillar 4, the demographically, right, we were just in a place where for the next few years it's going to be challenged. We have a kind of a naturally older workforce, and yeah, it's an issue, and it's one that has our attention, and we're addressing. And I appreciate the educators doing their piece of letting them know what all those pieces where I mean it's true. My first job out was as a researcher and doing spectrum sensing, and I had to know how to do a lot of code. We were pretty self-reliant on. We couldn't go hire coders. So yeah, all those are important pieces.
Wow, from a Department of Defense perspective, that's a really big question because we have a lot of needs, everything from our acquisitions, programs, which that's a little bit easier to understand, maybe the engineering technologies that we'll need. Some of the gaps that we see in that are we have key performance indicators in our different programs, and often those are not articulated well, and they don't consider all the spectrum type issues, the spectrum dependencies, and those kinds of things. So, at the engineers type level, having folks that are able to not only understand the science, but then help us translate that into effective key performance indicators for the acquisition. But then I go all the way then to the operational side, and I look at having an individual that understands just general military planning and how then to fit spectrum considerations into military plans. And so then you need all of the military appreciation for planning horizons from current ops to future ops to deliberate plans, and how those little factors fit in. So you have to be able to think from strategic to tactical level and understand the outputs at each of those different levels. So there's a lot. And so we definitely struggle with that within the Department of Defense, building all the different courses and the series of experiences that somebody needs to be effective in articulating all that. And at my level, I'm seeing gaps all the way from engineers at the acquisition side all the way to our operators. So there's a lot to do.
So I would just say, always ask yourself if you're still solving the right problem. You start as an engineer, you start working on a problem, you get a box drawn, there's assumptions that go in the box. And as new data comes in, or as different thoughts come in from other fields, you need to think about, am I just sitting in the box, or do I need to think about how all of that data should really be changing what I'm doing and changing the direction? So always step back and think about if circumstances have changed and you actually need to be shifting the direction of the project you're working on.
I guess just to add to from the FCC's perspective, we're obviously looking for new bright individuals to work at the FCC. We also cover a large, diverse set of backgrounds. We've got an honors engineering program. There's actually an open posting right now currently on USA Jobs. There's an honors attorney program as well. We have both paid and unpaid internships. You heard about all of our economists at the earlier keynote if you were there. So we've got a lot of different backgrounds, and we're there are always new postings on USA Jobs. So, do we have time for one more question, or are we? Maybe a quick. Okay. Do you all have any closing statements, or?
Just to say thanks for having us here, and thanks for listening today.
Yes. Yeah. Thank you to the organizers and
He's got a question there. So.
Okay.
I do,
All right.
and thank you so much for the time.
Yeah.
Mr. Mueller, in particular. So we talked about 7.11 earlier,
Right.
and we acknowledged electronic attack is defined. Spectrum sharing is not. Doesn't exist. Same thing with FCC regulations. I understand that there's a couple of different definitions that are floating around. DoD has a definition. This community has a definition. I want to suggest 7.11 is a great area where the treatment is different than all the rest of the Red Book, right? Because there's a certain expectation of experimental radio stations. Could we perhaps use both of those definitions, just maybe in different areas of the Red Book? I mean, really, there is confusion if at INL, if I try to do true dynamic spectrum sharing, it could be categorized as electronic attack, when that's totally not the purpose, right? Not trying to interfere with non-participating emitters, but I absolutely do need to overlay it in order for it to be spectrum sharing. So just want to plant
Yeah.
the thought.
No, I appreciate the comment. We do have to wrap up though, because we've got multiple parallel sessions going on. So anyway, thanks everyone for attending.